that of the resonating structure which has the lowest internal energy is called resonance energy. Though we have seen the so many applications of thermodynamics, there are some of the limitations in first law of thermodynamics. Entropy is a state function, hence change in entropy depends only on the initial and final state of the system. Here it is essential to introduce a new thermodynamic function called entropy. Hello everyone, this is Harshita Bhavasar from Vidhyaashram, PU College Temple of Excellence. Today we are starting up session 7 from the chapter Thermodynamics. In the last class, we have discussed about lattice enthalpy and Born-Haber's cycle. What is lattice enthalpy and how it will be measured with respect to Born-Haber's cycle, we have discussed in the previous session. In today's session, we will discuss about resonance energy and entropy, and also spontaneous and non-spontaneous process. Energy will be started from, with the help of driving force we will also see. First we will see what is resonance energy. So many previous chapters like organic chemistry, we have seen what is resonance energy. With respect to thermodynamics, how it will help, we will see. We know that a resonance hybrid is more stable than any single resonating structure. Yes, the resonance hybrid, which is the product of all the resonating structures, is more stable than single resonating structure. The greater the resonance energy, greater is the stabilization due to resonance. Whenever resonance is in high, that time the stability will be high. The difference between the observed heat of formation of the actual compound, that of the resonating structure which has the lowest internal energy, is called resonance energy. Once again, the difference between observed heat of formation of the actual compound and resonating structure. What is the actual compound and the resonating structure? Between them, the difference of observed heat of formation is called as resonance energy. Resonance energy formula, see here, observed heat of formation and calculated heat of that enthalpy of formation of resonating structure of the actual compound having the lowest internal energy. Observed heat of formation minus calculated heat of formation. The value of resonance energy of a resonance hybrid is not an absolute value, but it is a relative value. Yes, whatever the value of resonance energy from the resonating structure, it is not a real value because it is a single resonating structure, not a resonance hybrid. So it is a relative value. Whatever the value you will get from resonance hybrid, that is the actual value. Okay. For a few common physical and chemical process, the enthalpy change with required conditions are given below. Process, that is reaction. Here molar amounts of reacting as represented by balanced chemical equation. So enthalpy will be plus or minus. It may be positive or negative. Formation means the 1 mole of compound from its elements in their standard state. It may be also positive or negative with respect to enthalpy. Combustion means complete burning will take place. So only negative. Transition means allotropic forms, one form to another form. Transition of 1 mole of substance at its transition temperature and pressure, it can be positive or negative. Solution, dissolution of 1 mole of substance in large excess of solvent, that is plus negative or positive. Neutralization, 1 gram of equivalent mass of an acid neutralized by 1 gram of equivalent base in dilute solution, it gets neutralized, so negative. These are the conditions of enthalpy with respect to process and condition. Next one, limitations of first law of thermodynamics. As though we have seen the so many applications of thermodynamics, there are some of the limitations in first law of thermodynamics. All reactions in perfect agreement with the first law of thermodynamics may not occur. Whatever the statement has been given from the first law of thermodynamics, it will not applicable for all the reactions whatever we have seen. A tumbler of water kept in an ice bath does not get heated up by extracting heat from the ice. Although it may be conserve energy during the process, when a perfume bottle is opened, the perfume spreads uniformly in the room, but the reverse is not observed. Yes, when the perfume bottle, if you keep open, that fragrance will be spread out to the surrounding room or environment, but the reversible energy, can it come? No. And also whatever the heat is present in the ice, that will not move to the tumbler of water, right? Like that, energy can be observed but not in all the aspects. That's what they are telling. First law of thermodynamics does not indicate the direction of a reaction. This law will not indicate the direction of reaction. Anyway, it will be act. The extent of convertibility of one form of energy into another cannot be predicted by the first law of thermodynamics. The extent of convertibility means one form to another form, the states of matter will be converting. How much extent it will take, it is not defined confirmly. These two limitations have led to the framing of the second law of thermodynamics. By these two limitations only, it led to the formation of second law of thermodynamics. Major two is these two limitations. Next, spontaneous process. Heat flows from hotter end of a metal rod to the colder end spontaneously till equilibrium is reached. Means one metal rod is there, at the one end it's keep on heating, it moves to the other end of that cooled portion. At the spontaneously it will move till it reaches the equilibrium. Diffusion of gases occurs from a region of higher pressure to a region of lower pressure spontaneously until equilibrium is reached. In gaseous nature also same thing, from the higher concentration to lower concentration, gaseous will be keep on moving until it's in equilibrium. A process which occurs on its own without an external aid is called a spontaneous process. A process which occurs as a voluntarily without any aid, external aid, will be called it as spontaneous process. All natural processes are spontaneous and occur in a particular direction to reach the equilibrium. Whatever the natural process we can observe in the environment, all are spontaneous process. When it will stop? After it reaching the equilibrium. These aspects, direction of spontaneity and attainment of equilibrium, are better explained by second law of thermodynamics. All these aspects of spontaneous process and direction of spontaneity and also attainment of equilibrium, how it will reach for the equilibrium, these three aspects will be explained by second law of thermodynamics thoroughly. Here it is essential to introduce a new thermodynamic function called entropy. Entropy has been introduced here, the word. What does it mean? What are the functions with respect to thermodynamics? We'll see now. Before that, we'll understand non-spontaneous process. A process which occurs with the external aid is called non-spontaneous process, which will get instantly, it will call spontaneous without external aid. With external aid will be considered as non-spontaneous process. It is an unnatural process because intentionally we have to do, so that is unnatural process. A non-spontaneous process will not continue to happen without the external intervention. Suddenly or accidentally it will not happen like spontaneous. It waits for the external aid and it will continue till the external aid influence is there. Such a process has a positive free energy change. That process has a positive free energy. That free energy will be represented by energy change delta G equal to positive, and it is said to be an endergonic process. Okay. What drives a spontaneous process? For the spontaneous process, what are the driving forces? The force responsible for a process to be spontaneous is called driving force. Whatever the force is applied on the process, that will be considered as driving force for the spontaneous process. So, what are the driving forces for a chemical process? The tendency to attain minimum energy. Attaining a state of minimum energy means greater stability. We know this statement from the day one, that is, with the minimum energy, greater stability should attain for the stabilized chemical reaction. There are several processes that attain minimum energy, for example, exothermic reactions, but is liberation of energy in a process the only driving force of a chemical process? This may not be true, as there are several processes which are endothermic, but still are spontaneous. Examples of such processes are evaporation of water, which is spontaneous, dissolution of ammonium chloride in water, which is an endothermic process, but still happens spontaneously. Means what they are telling, there are so many or several processes that attain minimum energy. For example, exothermic or endothermic. In exothermic, the liberation of energy in a process only driving force of a chemical process. But always it is not true. It may be endothermic also, when the endothermic energy will be involved in the reaction, like example, dissolution of ammonium chloride in water or evaporation of water. In those it will happen spontaneously. Similarly, several irreversible reactions are observed in nature. In these reactions, both forward and reverse reactions takes place simultaneously, even though one of them is an endothermic reaction. There are so many other reactions also there. Simultaneously endothermic or exothermic reactions will take place, and also both forward and reversible also takes place. The tendency to attain maximum disorderness. Disorderness means the molecules will be not placed in a certain position. When we study such non-spontaneous processes which still occur even though the direction of the process is endothermic, we see that in most of them, the disorder or randomness increases. Examples may be the evaporation of water at room temperature, diffusion of gases from a region of higher concentration to lower concentration. Here we can talk about diffusion or evaporation of water. These are all the tendency to attain maximum disorderness or randomness of molecules. Okay. Next one, the entropy. Here it will be introduced. Entropy is a measure of disorder or randomness of the system. It is represented by capital S. Entropy is an extensive property. Okay, it is the disorderness or randomness of the system. Consider the following example. Two bulbs, one containing chlorine gas and the other bromine gas, which is green chlorine and other bromine gas in brown color, separated by a closed valve. We say that the two gases an ordered state. Once the valve is opened, the two gases mix spontaneously, increasing the disorder. As molecular disorder or randomness increases, entropy of the system also increases. What they are telling? Two bulbs are having, one is chlorine gas, another bromine gas with the closed valve. When it is opened, that valve, the disorderness or randomness of molecules will take place. Obviously, two gases will mixed. Whenever the randomness is getting increased, obviously entropy will also increase. Thus, water vapor has greater entropy than liquid water, which in turn has greater entropy than ice. Yes. In the gas, entropy is more because the randomness is more rather than liquid state or solid state. Entropy is a state function, hence change in entropy depends only on the initial and final state of the system. It is a state function and it is having extensive property. So, delta S equal to S final minus S initial. State function means it is depending on initial state and final state, not on a path. Next, for an infinitesimal change in S, that is entropy, change in entropy ds is defined as dq reversible by T, that is heat by T, temperature. For a measurable change in reversible process, change in entropy is given by Q reversible, that is heat reversible by T, where Q reversible is the heat absorbed by the system. Q reversible equal to delta H or delta U, means enthalpy, change in enthalpy or change in internal energy for isothermal process as well as non-isothermal process also. Next, energy of the universe is conserved, but the entropy always increases in a natural process. Energy of the universe is conserved, we know that, but entropy always increases in the process. Significance of the statement: whenever change in entropy of universe is greater than 0 for a spontaneous process, when the delta S universe total is equal to system entropy of system and entropy of surrounding. In an isolated system for a spontaneous process, delta S, that is entropy of system, is greater than 0. The entropy of a system increases up to equilibrium state and attains a maximum value. Therefore, a reversible process at equilibrium that is delta S equal to 0. Entropy is a state function and delta S is independent of path, that is delta S will be the same whether the change has been brought about reversibly or irreversibly. It is a state function and more than 0 entropy of universe is at spontaneous level, and entropy of universe means it will belongs to entropy of a system and entropy of a surrounding. In an isolated system, spontaneous process is greater than 0. Next, second law of thermodynamics. The entropy of the universe always increases in the course of every natural process. The entropy of the universe always increased in the course of every natural process. It may be spontaneous or it may be irreversible. Other forms of second law, various scientists have told what are the other forms of second law. All spontaneous processes are thermodynamically irreversible. That is one statement they have given. Every perfect machine working reversibly between the same temperatures of source and sink has the same efficiency irrespective of the nature of substance used in Carnot's theorem. This is the Carnot's theorem which will be in the engines they will use, okay, and it is impossible to obtain heat from a source or a hot reservoir and convert it into quantitatively to work in a cyclic process without transferring a part of heat to a sink, which is a cold reservoir said by Lord Kelvin here. One thing, all spontaneous processes are thermodynamically irreversible. Whenever the fast reaction is taking place, it cannot reverse, we know that. And also every perfect machine working reversibly between the same temperatures, that efficiency will be same or equal, but nature of the substance will be not. And also it is impossible to obtain heat from a source. You cannot obtain the heat from a source if it is having hot reservoir, and you cannot convert them into a quantitatively as a cyclic process also, said by Kelvin. Next, it is impossible for a cyclic process to transfer heat from a system at a lower temperature to one at a higher temperature. In a cyclic process, you cannot push from lower temperature to higher temperature without applying some work. That is true. From a lower to higher region, you cannot send anything in a cyclic process without applying any work. That was said by Clausius. In a reversible process, the total entropy of the system and surrounding remain constant while it is increasing in a irreversible process. Whenever in a irreversible process is going on, the total entropy of the system and surrounding remain constant while it increases in an irreversible process. In a nutshell, the first and second laws of thermodynamics can be summarized as follows. Energy of the universe is conserved, but the entropy always increases in a natural process. The conclusion for the both statements: energy is conserved, which was said in the first law of thermodynamics, but the entropy keeps on increasing in the universe. It was said in second law of thermodynamics, but both the statements are true only. See here, reversible isothermal process. First law of equation, that is internal energy equal to heat plus work. For Q reversible minus work reversible, work done will be minus. Here at isothermal energy, internal energy will be 0. W equal to nRT ln V2 by V1. We know that W reversible is equal to nRT ln V2 by V1. As delta U equal to 0, Q reversible nRT ln V2 by V1. At delta S system, that is entropy of a system equal to Q reversible by T, that is also we know, nR ln, that is V2 by V1 for reversible process. This T has taken here, you no need to write there T. Next, for a reversible isothermal process, heat absorbed by the system is equal to the heat lost by the surrounding. For reversible isothermal process, what they are telling, heat absorbed by the system is always equal to the heat lost by the surrounding. So, entropy of system Q by T and entropy of surrounding minus Q by T. So, total entropy of universe will be entropy of system plus entropy of surrounding. In case of an irreversible isothermal expansion in vacuum, No external pressure will be there, so work done will be 0, internal energy will be 0 and heat will be 0. The surroundings do not exchange heat. So that is entropy of surroundings will be 0 only. Entropy of universe total, entropy of system plus surrounding, that R ln V2 by V1. V2 will be always greater than V1, that is entropy of universe is greater than 0 always. Irreversible expansion in vacuum is spontaneous for expansion against finite pressure external pressure. See here, entropy of system is equal to heat reversible by T, that is entropy of surrounding, and heat at irreversible process by temperature. What will happen? As work reversible is greater than work irreversible, we can write as Q reversible is greater than Q irreversible with respect to heat they are telling here. So entropy of universe, what will happen? Entropy of system plus entropy of surrounding, heat reversible by T minus heat irreversible by T greater than 0. Therefore, irreversible expansion is a spontaneous process, not a non-spontaneous process. Next, relations for entropy change for specific cases. What are the relations for entropy in the specific cases? We'll see. Reversible isothermal expansion of ideal gas. Entropy is equal to heat reversible by temperature equal to nR ln V2 by V1 or P1 by P2 also you can write. At second case, reversible adiabatic expansion, their heat is always constant, it will be 0. Entropy is also 0. The increased disorderness caused by expansion of the gas is just balanced by the increased order due to the cooling of the gas. It will be same on heating or cooling. In the isobaric change, entropy is the difference between T2 and T1. Specific heat of constant pressure by temperature delta T, or here NCP ln T2 by T1. These are the conditions or relations for entropy changes for specific cases. Next, in isochoric, at constant volume T2 by T1, in between delta S will be there. At phase transition, solid to liquid or liquid to gas, enthalpy will be there, enthalpy by temperature. And entropy change of universe in irreversible isothermal expansion, this one we have seen many times. Entropy of universe equal to entropy of system and plus entropy of surrounding. Both if you write, it will be equal to 0. Note, the entropy change of the universe is 0, but the entropy change of system is positive. Overall, entropy of universe is 0, yes, but in the system it is positive always. Entropy change of universe in irreversible isothermal expansion, what will happen? Free expansion into vacuum. So, you have to use delta U equal to Q plus W. What will happen? V2 by V1, here delta U is also 0, Q is also 0, work done is also 0. So, it will be positive in the universe. V2 by V1 is greater than, if it is V2 by V1 is there more than 1 or V2 greater than V1, it will be having definite value. In an irreversible process, entropy always increases, therefore the entropy of the universe tends to maximum disorderness. Next, third law of thermodynamics. Unlike assigning relative values to energy and enthalpy with respect to the chosen standard, the absolute value of entropy can be calculated using the third law of thermodynamics. Here what they are telling, the relative values should be assigned for energy or enthalpy. Till it has been assigned, the absolute value of entropy can be calculated using third law of thermodynamics. The entropy of all perfect crystallization substance is 0 at absolute 0. At absolute 0, the perfect crystalline substances will be, which is having entropy is always 0. Next, enthalpy and entropy as criteria for spontaneity. Enthalpy change during a reaction could be positive or negative for a spontaneous reaction. For a spontaneous reaction, delta H or delta S, it can be positive or negative. Hence, the sign of enthalpy cannot be predicted by the spontaneity. Entropy change in the universe is positive for a spontaneous process. So, what will happen? Delta S universe, entropy of surrounding and entropy of system, what they are telling? Entropy change in the universe is positive. Entropy of system can be positive or negative depending on increase in randomness or decrease in randomness. As entropy of surrounding cannot be determined easily, entropy of system is not suitable criterion for predicting spontaneity. We cannot find out or we cannot determine the spontaneity of surrounding. So obviously the entropy of system is not a criterion for the spontaneity. Therefore, enthalpy alone or entropy alone cannot predict spontaneity. This situation paves way for the introduction of another thermodynamic function called free energy. Individually enthalpy or individually entropy cannot be determined. So there is another term we'll introduce, that is called free energy. We'll call it as Gibbs free energy also. Free energy of a system is a measure of capacity of a system to do useful work. To do useful work, free energy of a system will be measured. It is represented by G, measured in calorie or joules. It is also called as Gibbs free energy function or simply Gibbs free energy. Free energy of a system is defined as the maximum amount of energy available in a system during a process to do useful work. Whenever the work has to be done, within the system some energy will be remained to do the useful work. That energy will be used, call it as free energy or Gibbs free energy. It is related to enthalpy, entropy and absolute temperature. So G equal to delta H minus T into S. Note that absolute value of free energy cannot be given. It is a state function. For a measurable change in thermodynamic parameters, Gibbs-Helmholtz equation will be written like this. Delta G equal to delta H minus T delta S. What they are telling? It is a state function. It is not a path function. So Gibbs-Helmholtz equation will come. G is a state function and hence change in free energy during a reaction is given by delta G equal to summation of G in products and summation of G in reactants. The standard free energy change, that is delta G naught for a reaction, is the free energy change involved when the reactants and products are in their standard states. At the 1 atmospheric pressure, the standard free energy will be delta G naught for a reaction in a free energy change which is involved in reactant and also product side. And this is delta G naught for F for elements is taken to be 0. At constant temperature T, the standard free energy change is given by delta G naught equal to delta H naught minus T delta S naught at constant temperature. Next, significance of free energy. Consider the equation G equal to H minus Ts, free energy, enthalpy, temperature, entropy. But H equal to U plus PV, we know that G equal to U plus PV minus Ts. For this one, H will be U plus PV minus Ts, that they have written here. Upon differentiating, delta G equal to delta U plus PdV minus TdS at constant temperature and pressure, what will happen? By first law, du equal to dq plus dw and or du equal to dq plus dw expanding plus dw non-expansion and dw equal to minus pdv. The work done could be expansion or non-expansion one. The expansion work is pressure volume work, while non-expansion work could be an electrical work, that is minus dw electrical. So du equal to dq reversible minus pdv minus dw electrical. By second law, ds equal to dq reversible by t or tds equal to dq reversible. This is from first law, this is from second law. At the end, substituting the all the equations, dg equal to dq reversible minus dw electrical minus pdv plus pdv minus tds, what will happen? Delta g equal to minus dw electrical minus delta g equal to dw electrical at constant temperature and pressure. Okay. The decrease in free energy of a system is the reversible non-mechanical or non-expansion work done by the system. Therefore, in case of an electrochemical cell, Gibbs free energy change is related to the electrical work done in a cell by a reaction is delta G minus NFE equal to minus W electrical. This is At electrical cell, we can use this formula. If the reactants and the products are in their standard state, that is at 298 Kelvin and at 1 atmospheric pressure, then delta G naught equal to minus NFE naught. Free energy and spontaneity, consider the equation delta G equal to du plus PdV minus TdS at constant temperature and pressure. First law, we know this one, or dq equal to du plus PdV, the interchanging. At second law, ds equal to dq reversible by t. Equation 4 becomes dg equal to dq minus dq reversible. For a reversible process, dq is equal to dq reversible and dg equal to 0 in equilibrium. For an irreversible, dq is lesser than dq reversible and dg is lesser than 0 at spontaneous. These are all the cases. Delta G is negative means reaction is spontaneous. Delta G is positive means reaction is non-spontaneous. Delta G is 0 means reaction is in equilibrium. What all the things we have learnt, more than that these cases are important. Once again, free energy is negative means reaction is very much spontaneous. Positive means non-spontaneous. It is equal to 0 means it is in equilibrium. So in cases A and B, the reaction is considered only in forward direction only, not in backward direction. At equilibrium, delta G equal to delta H minus T delta S. If it is 0, delta H minus T delta S. So T is taken here outside at the LHS side, delta H by delta S, that is enthalpy by entropy. Conditions for spontaneity: if delta H is negative, entropy is positive, the overall will be negative. Spontaneous at all temperatures, that is example burning of fuel. Enthalpy negative, entropy negative, negative at lower temperature, positive at higher temperature, it is spontaneous and it is non-spontaneous. N2, formation of ammonia and freezing of water. Both are positive means one side positive at low temperature, negative at higher temperature, spontaneous, non-spontaneous and spontaneous. For melting of ice and calcium carbonate decomposes for calcium oxide and carbon dioxide. Enthalpy is positive, entropy is negative, both are positive. Non-spontaneous at all temperatures, that is oxygen giving to 3 ozone molecule. Gibbs energy change and equilibrium. Gibbs energy is related to equilibrium at constant as follows. This is Gibbs free energy minus RT ln K, or energy, that Gibbs free energy equal to minus 2.303 RT log K. We are converting to ln from log. This completes your thermodynamic chapter. We have seen the first law, second law and third law with the terminologies of thermodynamics with so many derivations. So I hope you have understood completely what I have taught today and the previous sessions. Thank you. We'll meet in the next chapter.